This is Chapter 13, Part 6, Kepler's Laws. Corresponds to Sections 4 and kind of 7 in your textbook. Kepler has 3 laws, so we'll go through each of them. Kepler's first law says that each planet travels in an elliptical orbit around the Sun, and the Sun is at one of the focal points. So this is what an ellipse looks like, and the Sun is at one of the focal points. So people used to think that the planets traveled in exact circles, but Kepler took tons of data and finally figured out that an ellipse fit the data the best. Kepler's second law is the law of areas. So it says an imaginary line drawn from the Sun to any planet sweeps out equal areas and equal time intervals. So if the time a planet takes to travel the arc on the left, delta T1, is equal to the time the planet takes to cover the arc on the right, delta T2, then this area is equal to this area. So essentially what this law is saying, and what's more important than the actual area information, is that the planet travels faster when it is closer to the Sun and slower when it is farther away. So here it goes like zip, pretty fast. Here it goes like not as fast. So this is a consequence of the conservation of angular momentum. Because there's no net external force acting on the Sun-planet system, angular momentum is conserved. So the angular momentum, if you recall, is L equals mvr. So here, r is less, so the speed is more, and over here, r is more, so the speed goes down. So angular momentum is conserved. This also just makes sense because the gravitational force is stronger when the objects are closer together. So at this point, because the planet is closer to the Sun is exerting a larger gravitational force. The gravitational force is causing the centripetal force, which means the object has a faster linear speed. Conversely, over here, the gravitational force isn't as strong because the object's centers are further from each other, so the speed won't be as fast. So you can think of this Kepler's second law as 2 things. 1, conservation of angular momentum, very important. 2, gravitational force is stronger when the objects are closer together. Kepler's third law is the one that we probably use most often in textbooks. And it says the square of a planet's orbital period is proportional to the cube of the average distance between the planet and the Sun. And we typically write Kepler's third law like this. However, we normally use this formula right here. So just as a note, for an elliptical orbit, you want to replace this r here with an a, and that's the length of the semi-major axis. We'll be going over what semi-major axis means on the next couple of slides. And the other equation that we typically use for Kepler's third law is V equals the square root of gm over r. That may look familiar from the energy videos that you guys already watched. So this is the expression for the velocity of an object in a circular orbit. So a couple of important things. Note that this m, both these m's, is the mass of the central object that is being orbited. The mass of the planet or satellite that is in orbit does not affect its speed or period. So if you recall from one of the previous videos, when you set the centripetal force equal to the gravitational force, the little m's of the object canceled out. So that's why this big M is the mass of the central object. And also keep in mind that r is the distance between the centers of the two bodies, not from their surfaces. So here's a couple pieces of information about ellipses. So we have our two foci, and the longest distance through the center is called the major axis, so that would be this whole thing right here, and then half of that is A, or the semi-major axis, and that's the thing that I told you on the previous slide you want to use instead of R for elliptical orbits. The shortest distance through the center is called the minor axis. That's this right here. And then half of that is the semi-minor axis, labeled as B here on the diagram. I haven't seen the minor or semi-minor axis being used all that often, so don't worry about that too much. Now, the eccentricity of an ellipse is defined as E equals C over A, C being the distance between the center of the ellipse and one of the foci. So for a circle, the eccentricity of the ellipse will be equal to 0. The range of values is between 0 and 1, and the higher the value of E, or the closer it is to 1, the longer and thinner the ellipse. So the sun is at one focus in an ellipse, and nothing typically is located at the other focus. The aphelion is the distance further away, and I usually remember aphelion because it starts with an A, and so does the word away. So if you add A and C together, you'll get the aphelion. So let's go back and look at that picture. So let's say this is, let's say this is our sun right here. If you do A plus C, you get the distance between here and here. And it's called an apogee when the orbit is around the Earth. The perihelion is the point nearest to the sun, and the distance for the perihelion is A minus C. And for an orbit around the Earth, this point is called the perigee. Okay, let's do a couple of sample problems. First, we have Comet Halley orbiting the sun with a period of 76 years. In 1986, it had a distance of closest approach to the sun, and its perihelion was a distance of 8.9 times 10 to the 10 meters. So we want to find the comet's farthest distance from the sun, the aphelion, and we also want to find the eccentricity of the orbit. First, let's visualize this. So we have the sun at the focus here. This distance is the perihelion, and then this whole distance is the aphelion. And we know that if you add the perihelion distance plus the aphelion distance, you'll get this whole thing across the center. Remember, that's the major axis. A is half of the major axis, so RP plus RA will be equal to 2A. Now, we have enough information to use Kepler's third law to find A. Remember, this is Kepler's third law. I just replaced that R with an A because it's an elliptical orbit. So I find these problems easier to do if I solve for the missing variable first and then plug in numbers. So the first thing I'm going to do is divide both sides by 2 pi. And I get that. And then I will square both sides. And I get that. Next, I'm going to multiply both sides by GM. and then I will take both sides to the 1/3 power. So I have A equals gmt squared over 4 pi squared, and all of that to the 1/3. So I want to use that formula to get A, but first, this period is in 76 years. We want things in standard metric units, and the standard metric unit for time is seconds, so we want to convert that to seconds. So I'm going to use some dimensional analysis because that just makes things easier for me. So there's 365.24 days in a year, there's 24 hours in a day, and 3,600 seconds in an hour. So that cancels out, that cancels out, that cancels out. And we end up that 76 years is equal to 2.4 times 10 to the 9 seconds. So on the previous slide, we derived our formula for A, or the semi-major axis, and now I just have to plug in numbers. Don't forget to square that period here. Oh, and just as a reminder, at this point, we have T being equal to a bunch of different things. In one of our units, we had T being equal to tension. T is kind of equal to torque, although generally we use Tal for torque. Remember, in this unit, T will be equal to the period for time. So make sure you're keeping your T's straight, depending on which type of problem you're doing. Okay, so once you plug in your numbers correctly, you should get that A is equal to 2.686 times 10 to the 12. And then we decided earlier that the perihelion distance plus the aphelion distance is equal to 2A. That was the whole point of us solving for A. So here I just plugged in the perihelion distance. We're solving for the aphelion distance. And when we do that, we get that the aphelion distance is equal to 5.28 times 10 to the 12 meters. Now, part B of the question asks us to find the eccentricity of the orbit. And if you recall some of the notes that you guys were supposed to take on this video, the distance for the perihelion is A minus C, and remember that the eccentricity is C divided by A. So the perihelion distance, excuse me, plus C is equal to A, and you can actually see that from our original diagram. Let me just go back to that real quick. So if you do this, the perihelion distance plus C, this being C right here, then that is equal to A. So if you solve that expression for C, you get A minus RP is equal to C. You can plug in your numbers. So we got A already, and the problem gives us RP. So we get that C is equal to 2.597 times 10 to the 12 meters. And we just say E equals C over A. So 2.597 times 10 to the 12 divided by 2.686 times 10 to the 12, and we get that the eccentricity is equal to 0.97. So that is a super elliptical ellipse, a very long and thin ellipse, and that makes sense because Comet Halley doesn't stop by too often. All right, let's do another example problem, and this is from the 1992 exam. So we have a spacecraft of mass 1,000 kilograms, and it's in elliptical orbit about the Earth. At point A, so right here, the spacecraft is at a distance 1.2 times 10 to the 7 meters from the center of the Earth, and its velocity is 7.1 times 10 to the 3rd meters per second. And that's perpendicular to the line connecting the center of the Earth to the spacecraft. The mass and the radius of the Earth are ME equals 6 times 10 to the 24 kilograms, and RE equals 6.4 times 10 to the 6 meters. So we want to determine each of the following for when the spacecraft is at point A. So for A and B, that's what we want to do. So A asks us to find the total mechanical energy. And it says, assuming that the gravitational potential energy is 0 at an infinite distance from the Earth. So that's just assuming what I taught you guys when we derived our formula for gravitational potential energy. And then we also want to find the magnitude of the angular momentum of the spacecraft about the center of the Earth. So here are parts A and B. We know that the gravitational potential energy is equal to this formula right here. That formula is in your table of information. So we plug in our correct numbers. So the mass of the Earth, the mass of the spacecraft, and this is the distance between Earth's center and where the spacecraft is. And we get negative 3.3365 times 10 to the 10 joules. Now the problem gives us the speed of the spacecraft, so that's nice and handy because it's an elliptical orbit. And remember, we can't use that one equation for elliptical orbits, only for circular orbits. So we have k equals 1/2 mv squared, m is 1,000, and the speed that we're given is 7.1 times 10 to the third. So we get 2.5205 times 10 to the 10 joules. The total mechanical energy is the kinetic plus the potential energy. We plug in the kinetic energy that we just got and the gravitational potential energy that we just got. And we end up with negative 8.16 times 10 to the 9 joules. So that is the answer to part A. And part B asks us to find the angular momentum when the object is at point A. And angular momentum is just equal to mvr, or that's one of our formulas for angular momentum. And that's the one we want to use here because the distance between the two centers is large. So again, the mass is 1,000. V is 7.1 times 10 to the third, and R is the distance between their centers, 1.2 times 10 to the seventh. So we end up with the angular momentum being equal to 8.52 times 10 to the 13 kilograms times meters squared per second. So that is our answer to part B. So there are also parts C, D, and E to this problem. So it says later the spacecraft is at point B on the exact opposite side of the orbit at a distance RB equals 3.6 times 10 to the 7th meters from the center of the Earth. So we want to determine the speed VB of the spacecraft at point B. Then suppose that a different spacecraft is at point A at that distance 1.2 times 10 to the 7 meters from the center of the Earth. And so it says this, we want to find the speed of the spacecraft if it is in circular orbit about the Earth. So it'll be different from our original spacecraft because it's in circular rather than elliptical orbit. And then we also want to find the minimum speed of the spacecraft at point A if it is to escape completely from the Earth. So, part C is determine the speed of the spacecraft when it is at this point. So here is where we want to use the information we know from Kepler's second law. We know that the speed here is going to be faster, and over here it's going to be slower because angular momentum is conserved. So the angular momentum it has at point B at that further distance is going to be equal to the angular momentum it had at point A, that closer distance. Now, we already know the angular momentum at point A because we were asked to solve for it in a previous part of this problem. So the angular momentum at point B is mvb/rb, and that's equal to 8.52 times 10 to the 13. We know that the mass of the spacecraft is 1,000, and we're given the distance of the spacecraft at point B, how far it is from the Earth's center. So we just plug in those numbers and solve for VB. And we get that the speed of the spacecraft at point B is 2.37 times 10 to the third meters per second. All right, and then part C, we want to find the speed of the for part D, we want to find the speed of the spacecraft if it's at point A, but this time if it's in circular orbit. Now, I don't know about you, but I don't really remember the equation we derived for an object in circular orbit, and it is not given to you in your table of information. So I would know how to derive this. Recall that the gravitational force is causing the centripetal force. So that's just gmm over r squared equals mv squared over r. So the m's cancel out. One of these r's will. And we end up with gm over r equaling v squared. If you solve for v, you get the square root of gm over r. Now, we know that the mass of the Earth is 6 times 10 to the 24, and we know that the spacecraft is a distance of 1.2 times 10 to the 7th meters from the Earth's center. So we just plug in those numbers, and we get that the speed is 5.78 times 10 to the third meters per second, which again is different from our given value of 7.1 times 10 to the third meters per second. So this is if it's in circular orbit. The other one was elliptical orbit. Now part E asks us to find the escape speed when it's at this point. So basically, what speed would that spacecraft have to be given to completely escape from the Earth's pull? Now, we did do this video pretty recently, but I'm going to derive the expression again, because again, it's not given to you on your table of information, so it's worth knowing the concept behind it. So, at an infinite distance from Earth, which would be the escape distance, if you want to call it that, the kinetic energy will be equal to 0, and so will the potential energy. So the kinetic energy plus the potential energy will be equal to 0. And our expression for kinetic energy is 1/2 mv squared. For gravitational potential energy, it's negative gmm over r. So if we divide all of the sides by m, and then the m's just go away, and we end up with 1/2 v squared equals g times 6 times 10 to the 24. That's the mass of the Earth. And then r is the distance between the spacecraft and Earth center. We solve that for v, and we get 8.17 times 10 to the third meters per second. So that's the speed that you would have to give the spacecraft when it's at that point in order to get it to completely escape from Earth's pull. So that problem didn't have all that much to do with Kepler's laws, but we did have to use a lot of the information we've learned from in previous videos.